This evening's topic is linear programming. What is linear programming? We're going to use linear inequalities to figure out ideas. And so linear programming is the process of optimizing a linear objective function subject to a system of linear inequalities called constraints. The graph of the system of constraints is called the feasible region. I know this doesn't make any sense right now. Just bear with me. To optimize, however, is to find the maximum or minimum values of some quantities. Okay? And I'm going to do this by looking at these inequalities, and I'm going to see where they intersect. An objective function has a maximum and minimum value, then it must occur at the vertex. So we just have a certain few points to check. It's going to be our vertices of the feasible region. Moreover, the objective function will have both the maximum and minimum value if the feasible region is bounded. And if it's not, it may not have a maximum, or it may not have a minimum, or it may not have both. We're going to look at that in our second example. So let's look at our first example. Example 1. These are not in your course pack. You can print out the notes ahead of time. Hopefully you did that by now. Find the minimum value and the maximum value of this c equals 3x plus 4y. This here is my objective function. Everything I'm talking about comes back to this function. This is my primary function. Now, the constraints for this function are x is greater than or equal to 0, y is greater than or equal to 0, x plus y is less than or equal to 8. Those are my constraints. Okay? So what I first want to do is I want to graph my constraints. X is greater than or equal to 0. So x is 0. Y can be any number I want it to be. So my first constraint, x is greater than or equal to 0. So I'm going to want the numbers that are to the left of the y-axis. Remember, this is the y-axis, this is the x-axis. X is greater than or equal to 0 is going to give me the y-axis. I know this, but this is what it looks like. Now, I'm not going to do the shading in just yet, but I do know that this is the part of the graph that I want. I want what is to the right greater than or equal to 0. Make sure I have my entire line. Now, y is greater than or equal to 0. That means I want all y's that are greater than or equal to the x-axis. So again, I'm going to want everything that is greater than the x-axis. So my region that I would shade is above the x-axis. Again, that's y greater than or equal to 0. I'm not going to leave it shaded. I know that essentially I want quadrant 1 so far. Let's look at my other constraint. My third constraint is the equation x plus y is less than or equal to 8. So I'm in quadrant 1. So I want x plus y is equal to 8. Excuse me, is less than or equal to 8. But I'm going to use x plus y is equal to 8 to figure this out. I could solve this for y and look at slope-intercept form. I am going to find my intercepts. So first I'm going to find my x-intercept. So I'm going to let y be 0. If y is 0, my x-intercept, let's try that again, x plus 0 is equal to 8, so x is equal to 8. That's my x-intercept. My y-intercept, I'm going to do the same way. I'm going to let x equal 0, and so it's going to be 0 plus y is equal to 8, so y is equal to 8. So my intercepts are 8, 0, and 0, 8. 8, 0 is the point 1, 2, 3, 4, 5, 6, 7, 8. 0 is here. 0, 8 is the point 1, 2, 3, 4, 5, 6, 7, 8. 0 is up here. So then my line that I want is going to be this blue line that connects these two x and y intercepts. I then need to notice that I want less than or equal to. All of my lines are solid lines because they're all equal to. Remember, I wanted to the right of the y-axis, and I want above the x-axis, to the right of the y-axis, and above the x-axis. And since I have less than or equal to, I want below x plus y is, I want below this point. If I plug in 0, 0, I get 0 plus 0 is less than or equal to 8. That's a true statement. So I know I want below since I picked that point there. And this is the graph of my region, which includes the x-axis, which includes the y-axis, and includes that blue line. This is my bounded region. Where are my notes? And if we go up a page, this is my feasible region. The feasible region is what I shaded in black that is bounded by the blue line, the x-axis, and the y-axis. This is my feasible region. Okay, so now I have my feasible region. I need to find my critical points. My critical points are my vertices. They're always vertices. They're always the vertex where my lines come together. My vertices are the 3 points, 8, 0, where I cross, where my line crosses the x-axis, 0, 8, where my line x plus y is less than or equal to 8 crosses the y-axis, and my origin, where my two axes come together. Where am I going to try out my vertices? I'm going to try them out in my objective function. So I'm going to write down here, c is equal to 3x plus 4y. And I want to find the maximum and minimum of these critical points. That'll find the maximum and minimum of the entire region. So try the first one. Okay, so I have 3 times 8 plus 4 times 0 is equal to 24 plus 0, which is equal to 24. My first C is 24. That's one of my points. Let's try another one. My next one is C is equal to 3x plus 4y. So C is equal to 3 times 0 plus 4 times 8, which is 0 plus 32. So C is equal to 32. That's my second critical point. And lastly, I'm going to plug in C is equal to 3 times x plus 4y. So C is equal to 3 times 0 plus 4 times 0. So C is equal to 0. From this, I can find that my maximum is 32, and my minimum is 0. So I found my feasible region and I graphed it. I found my critical points, which were 8, 0, 0, 8, and 0, 0. And then I found my maximum and my minimum, which optimized, again, we're using the word optimized, my objective function. So I did my linear programming. My maximum and minimum values are 32 and 0. And depending on what you're talking about, you can say it's 32 this or 0 that. And we'll see more of that tomorrow. So let's try another example. Example 2. Find the minimum value and maximum value. Optimize this objective function. So again, I have the objective function 5x plus 6y. Again, this is my objective function. Okay, and now I have 4 separate constraints. I need to use all 4 of my constraints. So the first thing I want to do is I want to graph these. X is greater than or equal to 0, so I want all x's that are greater than or equal to 0. Y can be whatever I want it to be. So that is going to be, again, to the right of the y-axis. Y is greater than or equal to 0. That means I want all my y's that are greater than or equal to 0. So I'm going to have everything that's above the x-axis. So at this point, looking at what I was just told, these two tell me that I'm going to be in quadrant 1. Okay, so I'm in quadrant 1. Notice that's all I gave you, so I knew that ahead of time. But I'm going to be in quadrant 1. Now I have 2 equations that I need to find. I need to go ahead and graph. So the first equation is x plus y is greater than or equal to 5. So I'm going to find my 2 intercepts because I'm using my x and y axes. So my 2 intercepts are going to be, my x-axis is something 0. My y-intercept, is 0 something. So I plug in 0 for y, and I get x is greater than or equal to 5. So this is 5. I plug in 0 for x, and I get y is greater than or equal to 5. So this is y. So my first my third line, I have the 5, 0, 1, 1, 2, 3, 4, 5, and 0, 5, 1, 2, 3, 4, 5. This is a red line, so let me choose a red line. Okay, so there's my third line of constraint. Notice for this one, I want greater than 5. If I plug in the point 0, 0, my origin, 0 plus 0 is not greater than or equal to 5. So for this line, I'm going to want what's above this line. So I want all of quadrant 1 that's above this line, but not what's inside that little triangle. And that's how this is different from the other one. Again, I know that I want this entire region over here right now because I wanted what's right of my y-axis, I wanted what's above my x-axis, and I wanted what's above this line here. So I know that I want this region up here so far. Now I need to look at my fourth constraint. This one was in red, and so I'm going to do my last one. Check that. Sorry about that. I'm on this page over here. I'm going to do this last one in black. And so this is 3x plus 4y is greater than or equal to 18. I want to find my x and y intercepts. So again, my x-intercept is when y is 0. My y-intercept is when x is 0. Plug in 0 for y. You get 3x is greater than or equal to 18. So x is equal to 6. Plug in 0 for x, and I get 4y is greater than or equal to 18. So y is greater than or equal to 18 over 4, which is 9 over 2, which is 4.5. So again, I'm in black in this one. So I want 6, 0, 1, 2, 3, 4, 5, 6, 0, and 0, 4.5. So 0, 1, 2, 3, 4.5. Let's get a black line for this one. And that is the line that I want. Let's try the point here that I've been trying, 0, 0. Let's do a different color, 0, 0. If I plug in 0, 3 times 0 is 0, plus 4 times 0 is 0, 0 plus 0 is 0. That is not greater than or equal to 18. So again, I want what's above this black line. So my feasible region, and I'll use the eraser again, is what's to the right of the blue line, right of the y-axis, what's above the green line, what's above the x-axis. I want what's above this red line and what's above this black line. So I end up with this region, and I'm going to do it in blue, that goes along the y-axis, goes along this red line. At this particular point here, it changes to the black line. At this point here, by the way, this point here was also important. Now it changes to the x-axis. So I'm going to do those critical points in red. So my region is along the x-axis. It's going to get this critical point here. It's going to go along the red line to this critical point, along the black line to this critical point, and then along the x-axis there. So all of this is my feasible region. But my critical points, and now here's a third color, are 1, 2, those 3 intersection points. Yes, I agree that this one, let's do these in a different color. These 1, 2, 3 points in red are where lines cross, but they're not part of the feasible region. So in green are my critical points, 1, 2, 3, because they're in the feasible region and they're critical points. So those are the 3 points I need to find. I do know that this top point up here, we already counted as 1, 2, 3, 4, 5. That's the coordinate 0, 5. I do know that this point over here is 1, 2, 3, 4, 5, 6, is the coordinate 6, 0. Now I need to find this coordinate. I could guess and try to count over, but this is where these two equations intersect. So I could actually kind of use what I did for systems and solve where these two lines intersect. I can solve them both for y and put them into my calculator and find their intersection point. I can use linear combination. What I'm going to find is that their point of intersection is the point 2, 3. I know that you can go ahead and find that, but I'm giving that point to you. So these are my 3 critical points because these are 3 critical points that are in the feasible region. So I have to check these against my original equation, my objective function. My objective function is c is equal to 5x plus 6y. And I have to check these 3 points because I want to find the maximum and minimum. So c is equal to 5 times 2 plus 6 times 3. So this is 10 plus 18, or 28. That's my first point. My second point, c is equal to 5 times 0 plus 6 times 0. So c is equal, let's try that again. I am doing the point in red. So c is equal to 5 times 0 plus 6 times 5. So c is equal to 30. And last is the point in blue. C is equal to 5 times 6 plus 6 times 0, which again, c is equal to 30. So if I look at my feasible region, I know I have a minimum here of 28. But if I look at this, this 30 and this 30 don't seem to me like they're going to be maximums. What if x was not 6, but 7, 8, 9, 10? What if I use the point 10, 0? Well, the point 10, 0 is going to give me 5 times 10 plus 6 times 0, and that's going to give me a maximum, or excuse me, give me a point of 50. Now that's above my two 30s. Now this is confusing. I know I'm confusing you. The very first slide says that the maximum or minimum values must occur at vertices if it's a bounded region. Go back to the third slide. This is not a bounded region. So I do have a minimum, and my minimum is 28. Can't spell minimum. Minimum of 28 at the point 2, 3. But there is no maximum. Because the region is not bounded. We will be working on this idea for the next 2 or 3 days, so relax. We will talk about this in class. We'll do more examples. There are problems in the course pack, but this is your first look at linear programming. Have a good day.